Welcome to the deep dive. Ever look at stats and wonder, well, how much can you really trust them?
Right, all those numbers flying around.
Exactly. So today, we're diving into confidence intervals. Think of it as a quick guide to understanding data reliability. Why those plus or minuses figures actually matter.
They're super important.
We'll hit questions like, how solid are our data estimates, really? And maybe more practically, what can these intervals tell us when we're comparing groups? Like, say, two different marketing approaches.
Yeah, they help answer exactly that kind of thing. So confidence intervals, they basically give you a range of plausible values, not just one single guess.
A range, okay.
And what's interesting is this trade-off, between how sure you want to be and how, well, wide that range ends up being.
Ah, okay. Like, if I want to be really, really sure, say 99% sure, I need a wider range.
Precisely. That 99% certainty demands a wider interval. You're more likely to capture the true value, but your estimate is less precise.
Less specific.
Yeah. But a narrower interval, maybe 90%, gives you a more specific range, but, well, you're less confident it actually contains the true population value.
So it's this balance act. Certainty versus precision.
Yeah.
Okay, what about just getting more data? Does that help narrow things down?
Oh, absolutely. Increasing your sample size usually shrinks the width of the confidence interval.
Ah,
Think of it like getting more information. The more data points you have, the more evidence you have, the more precise your estimate can be, usually leading to a narrower, tighter interval.
right. That makes sense. More data, more clarity. Now, here's something that always trips people up, myself included sometimes. A 95% confidence interval. Does that mean there's a 95% probability the actual population mean is inside that specific range we calculated?
Yeah, that's a really common misunderstanding. It sounds intuitive, but it's not quite right.
Okay, help me out here.
So the 95% probability refers to the method we use to create the interval. If we were to repeat the whole sampling process many, many times, say 100 times, we'd expect about 95 of those calculated intervals to contain the true population mean.
Ah, okay. So it's
Yeah.
about the long-run success rate of the method.
Exactly, not about the probability for any one specific interval you happen to calculate.
Got it. That clicks. Now, sometimes we don't know everything about the population, like how spread out the data is, the variance. Does that change things?
It does. When the population variance is unknown, which is, let's face it, pretty
It's
common,
usually the case, yeah.
or we have to estimate it using our sample data, this adds a little extra uncertainty. So instead of using the standard normal distribution or Z distribution, we use something called the T distribution.
The T distribution.
It looks similar, but it has slightly fatter tails, basically accounting for that extra uncertainty that comes from estimating the variance.
Makes sense. Adapting the tool. What about the foundations? What needs to be true for these intervals to even be, well, valid?
Yeah.
Any key assumptions?
Yeah, there are a few. Crucially, you need a random sample. The data should ideally represent the population you're interested in.
Okay, random sampling.
And then for intervals around the mean, we usually assume the sample mean itself is normally distributed. This can happen if the original population data is normal, or if your sample size is large enough thanks to something called the central limit theorem.
Right, the large sample size safety net. Okay, we've mostly talked averages or means. What if we're looking at percentages, like the proportion of people who click an ad?
Good question. The core idea is the same, finding a plausible range. But the mechanics, the formula, it's different. It's tailored for categorical data, yes-no type things, using the sample proportion.
Different formula, same goal. And I saw this term bootstrapping mentioned. Sounds interesting.
Yeah. It's a really powerful technique, actually. It's a type of resampling. Imagine you only have your one sample. Bootstrapping basically involves repeatedly drawing new samples from your original sample with replacement. You do this thousands of times.
Okay, resampling your own sample.
Exactly. And by looking at the variation in the statistic, like the mean or median across all those bootstrap samples, you can build a confidence interval without needing strict assumptions about the original data's distribution, like normality.
Wow, that's pretty neat, kind of making more data out of the data you have.
Yeah.
In a clever way.
It's very useful, especially with complex data or when assumptions are shady.
Okay, shifting gears slightly. Comparing two groups. Let's say we have confidence intervals for the average score in Group A and Group B. What if those intervals overlap?
If the confidence intervals for two independent groups overlap, it generally suggests there isn't strong evidence of a statistically significant difference between the population means of those two groups.
Suggest no difference. Okay.
Right. But it's not a formal test. Non-overlapping intervals might indicate a significant difference, but overlap definitely leans towards no significant difference found. You'd usually want a specific test for the difference itself.
Gotcha. So overlap is a hint, not the final word. What about the margin of error we hear about, especially in polls?
Ugh, the margin of error. It's simply half the width of the confidence interval. It's the plus or minuses value you add and subtract from your point estimate, like your sample mean or proportion.
The plus or minus bit.
Yeah. It tells you the maximum likely difference between your sample result and the true population value at a given confidence level. It's influenced by that confidence level and the variability or standard error of your statistic.
So smaller margin of error means more precision.
Exactly.
And finally, why calculate an interval specifically for the difference between two means? Why not just compare the individual intervals?
Because looking directly at the confidence interval for the difference is a more direct way to assess if that difference is statistically significant.
How so?
Well, if the confidence interval for the difference between two means contains 0,
Huh?
that means 0 is a plausible value for the true difference, which implies there might be no real difference between the two population means.
Ah, I see. If 0 is in the range, no significant difference.
Precisely. But if the entire interval is positive or entirely negative, so it doesn't include 0, that provides stronger evidence that a real difference exists between the groups.
That's much clearer. Okay, so to wrap up, confidence intervals give us that crucial range of possibilities around an estimate. They depend on how sure we want to be and how much data we have. Really vital for understanding uncertainty.
Absolutely. They stop us from putting too much faith in a single number.
Definitely. So thinking about all this, where in the real world is understanding that margin of error, that plus or minus, just absolutely critical before you make a decision? Maybe think about medical results or policy based on surveys. It really changes how you look at data, doesn't it? Something to ponder. Thanks for this deep dive.